Okay. So walk us through it. So what exactly are you doing?
In order to move all zeros to back, I need to create two variables, one temporary and one count, in order to count every number which will switch with the zero. So in the for loop, I told that if I not equal to zero, I gave to temporary variable. In first case, it nothing changed. This construction, but when I can make it just debug. Yeah. For loop. Oh, it's
You're on different
another. Yeah. Yeah, I was confused. This one. Just a second. Why is now debugging? Okay, I don't need this debug. So you see, first I just if I check if first number not equal to zero, I give to temporary variables. In this case, number count here is zero. Then I gave to this variable to in this case to one. I assign it to in this case one. It's one. As I mentioned before, it's nothing changed in first loop. And then I just need to assign to number I temporary variable. In second loop, we we didn't go inside the loop because it's zero. Then in case of two, temporary variable here it's one. That's why we save it to temporary variable this zero. Then we go and to switch these two with zero. And here, yes, it's with switching to in first index and zero to second index. And we make count. After that is also zero. We didn't go inside the loop. Then 4, and it was 1 2 0 0 4, and then 4 we also swap with the 0, and we have inside as a result we have 1 2 4 0 0 0, I believe.
And you ran it right, it works. Sure.
Yeah.
What happens?
1 2.
Yeah, what happens if you put two zeros? So if you change your integer array, add another 0. So like if you can make it 1 0 0 2 0 4 6.
1 0 0
Yeah,
2 0.
yeah,
Like that?
that's yeah. Just add a so repeating the zeros. Is that still gonna work?
It works.
Okay, okay.
Can you, excuse me, can you add after less zero another number?
After last one?
Yes, after last one.
We're all trying to break it, Sophie.
Mm.
We're all evil.
Because, I put some numbers and it doesn't work for me. Maybe I did something wrong. I'll check.
Yeah, I play with it
This is
a
good.
lot of time.
This is
Oh
good.
yeah, I put length -1 is my catch.
Here?
Uh-huh.
Yeah, we also can do it with 2 for loops, but Igor told us to make it with 1.
Yeah. So to your point about the ON, and the speed, the what you did, a single for loop is much faster, right? So you have that linear time ON, and if the double loops, you basically going 2 times against the length of the data element. So that's ON square usually. So since you asked earlier, so usually in nested loops or 2 loops is ON squared time. So try to certainly use a single loop if you can, just faster code. But yeah, this is good. I thought for some reason, because I'm looking at the logic, I thought that if we have 2 zeros, it doesn't work, but I don't know why.
Yeah, I think it works when we make first switch. Here we have 2 and here we have 2 zeros. In this case, it works. That's why it works. And with
Sounds
this.
like you tested it pretty well. So yeah, it's good. It's just numbers temp. I would suggest for readability, just naming the variables a little bit, because in this case, it's you obviously know what you're doing, but not temporary, but try to, and you don't have to do it right now, but try to figure kind of depict what they actually mean. And I know in this case, it's a little, when you're like running a loop and you're just trying to remember a number, sometimes it's a little hard, but when we read it, it's not as easy to figure out what's going on when you're just having like temp and stuff like that. So that's my only
And how would you offer to
so the temporary, what does that represent? So you're saving a number into a temporary. What do you describe that number? Is it a number, like, for example, is it number to shift, a number to do something with, right? So that's what I'm kind of referring to. How would you, so instead of temporary, how else could you name it? What does that number hold? What does the variable hold?
We just created in order to save. This variable and
right,
not close it when we switch it.
Okay, so we are going through, so let's go through this logic. We are going through an array, right? In plain English, we're going through an array. If we check in for any numbers that are not 0, we are saving the number to switch it later. Is that correct? For any non-zero number, we're saving the number to do what with?
This number, it's not 0 number.
Right.
Not 0 number, it's I. In this number, it's it will be index of number is not 0 number.
Well, so the temp is not the temp is actual number, right? It's not an index.
Temp, yes. Yes,
Yeah.
it's number.
So let's rename the temp to, so this is a non-zero item to remember or something, right? I guess is that, although it's a little lengthy, but maybe just something, non-zero number, something like that. Just a little bit, yeah. Yeah, so like I think that's just yeah, so okay, so then we do this. Maybe we can improve it later once we all run this turn. So numbers, okay, fine. So numbers, so let's do the count. What does the count represent?
Count
Okay.
represent the index
Mhm.
of a number which is not zero.
Okay, index of, so let's rename it that way, right? Because the reason is we already have an I index, and if we have count, it's a little hard to, keep track of both when you're reading this, right?
Mm-hmm.
You see what I mean?
Yeah.
So just anything that's a little bit more descriptive. So index of non-zero. Okay, that's perfect. That works. Index of non-zero.
And here we increasing it in order to go one by one. 1, 2,
Mhm.
0, 1, 2, and all non-zero numbers go one by one,
Right.
not separated with zeros.
Okay, and then you're doing the swap here. So numbers index of non-zero equals numbers I. So for any number that's not zero, index of numbers equals numbers I. Yeah. I'm trying to think how to maybe make that a little bit more descriptive, so that the whole goal here is just to have anybody be able to read this code without so um zero number.
It's a bit confusing because two
Yeah.
variables, no variables, yeah, we have to create here.
Yes, but that's the trick, right? It's not easy, but once you kind of have it a little bit more descriptive, that's where it becomes much easier to read, because it's what you're doing here is pretty cool, right? You solved it in a for loop, but it's a little hard to understand without debugging. So
Yeah.
um,
And also, I saw that on interviewer, sometimes they ask to swap some numbers without creating any temporary variables. And I think, how can we do it without creating any additional variables in order to save some variable in order not to lose it?
Is it yeah, I'm not sure.
I need a particular example. Yeah, I just saw it.
Yeah.
I think that it will be difficult.
Yeah, yeah. If you have any specific examples, definitely bring in.
Yeah, if I'll find,
together.
I'll send you.
Yeah, usually what's it could be a question on the interview is doing the shifting numbers in the array without creating a new array, right? That's kind of what I asked you guys to do. Make shift the zeros, but not creating another array. So that's a common thing. So but then you use I'm not sure how to swap two numbers in the array and not creating a new array, but not using a temp variable. That's you can probably try to shift the number like before or after the number you're trying to shift, and then mess around with indexes, right? So you remember, like, if you're trying to shift two numbers without creating a temp variables, you take the first one and maybe insert it before the target number, and then take the target number and insert it in the first slot. But you have to remember those indexes. So something like that, I guess. It just kind of remembering the indexes where you're inserting. But yeah, feel free to bring an example. We can.
Okay.
But yeah, this is good. So if you can, a challenge for you, just give it another thought, and try to make it so that it reads beautifully, right? So just give it a little bit more thinking how you're doing, what you're doing, and maybe next time you can show it to the class and kind of make it a little bit more kind of descriptive. So
Okay.
Excellent job. Thank you so much.
Thank you.
Yeah. And that's kind of the reason we're learning, the good coding practices, so you guys can, do this stuff and have your code. That's what differentiates senior developers, right? As you're going through and gaining more experience, that's what differentiates senior developers. They write code that anybody can just come in and read. So, and it's not easy, right? Sometimes in this simple examples, when you don't really have a lot of meaning to the variables, it's not easy to just change from like count or int like I to something meaningful. But that's a trick. That's where it values the most, because when you're naming variables like amount, tax amount, yeah, that's easy. But in this small loops, that's where it matters. So
yeah, it wasn't even easy for me to read and understand my own code.
Yeah, so it's it works, and that's half of the battle. So thank you. All right, any other questions on the homework? Well, you guys find time to finish it, and certainly let's take advantage of these opportunities to do a code review with the class, and that's how we learn how to do things and polish it. All right, so for today, the agenda is I'll have you guys take a break from all the coding exercises for a bit. So I want to finish the data structure class, but we're not going to be completely finished. It's just still things going to come up in our algorithm topics, but I want to talk about the kind of the final the data structure I wanted to cover, and it's going to be trees. So I'm going to cover that a bit. I'm not going to get in a lot of details. Trees are a little bit more advanced, and we're going to talk about trees more when we talk about algorithms, so tree traversal and that type of stuff. But at least you'll get an idea what trees are. And also today I wanted to give you an introduction to, so next set of classes on Thursday, we're going to be talking about algorithms. So algorithms are, and data structures, they go hand in hand. Algorithms are, also a huge part of interviews. So you already probably heard about different searches, binary searches, divide and conquer techniques. It also comes on the interviews, sorting, searches, that type of stuff we're going to be covering. So we're going to cover all the main techniques that you can use for your day-to-day, programming jobs in the future, as well as interviews preparation. So, all right. So that's the agenda. Let me just admit person here. Okay, so let's jump to the slides, and I will talk about trees. I assume you guys are going to be familiar with that, and even if you haven't dealt with that, all of you have social networks, and that's kind of what trees represent. You and your contacts. It's a perfect data structure because, as you may imagine, if you have to have some type of structure to represent, your contacts, context of your contacts, and so on. That's where the trees come in, because you can't really represent that in the in a linear data structure that we've been discussing, right? Arrays and array lists and all of the other things are not really suitable to represent relationship, and that's what we are representing with trees, and that's really the relationship type of data. So an element could have one or more children, right? So in a kind of a LinkedIn, you are kind of the head element, right? The node of the head node of the tree, and then you're gonna have basically your children, which are your contacts, and each contact, they have their own context. So those are kind of in a tree data structure, they're called children, but they're not really children. Obviously, they are just something that relates to you, right? Like children relate to a mother and a father. So that's kind of what the trees are. So again, nonlinear data structure as opposed to linear, like arrays, right? One item after another. Trees are really a collection of nodes, so it's a hierarchy, and basically it's a each node in there, each element in the tree it has a value, right? And the value could be anything. It could be a data object, right? It could be like your LinkedIn profile, your LinkedIn object with all the information that they have on you, like all the attributes, your jobs, your experience, your interests, your endorsements, and then they're pointers to the children. And in the LinkedIn example, it would be your contacts, like the ones that you are directly related to, right? So you're related to them, like following them and that type of stuff. And they are in turn, they would have pointers to their children, which are contacts that they are following or connected to, right? So that's kind of the relationship in a real world example. So nodes are connected by edges, and we'll talk about it in a bit. I'll kind of show you the actual structure. Trees are one of the most powerful advanced structures. So arrays and lists and all of that stuff, you're going to use it probably 99% of your time for the stuff that you do, but it has obviously, as you know, limitations, right? It can't really represent relationships that easy, because you can loop through an array or linked lists or array lists or anything like that, or even hash table, right? Hash sets and all those things, but they don't really have relationship. A loop just represents kind of a linear structure, so you can't connect number element 2 of the array to element 22 directly. They're linear, right? So you can't really connect them and so on. So it's a big disadvantage, but you don't necessarily always have to have that ability, but that tree provides. But it's a powerful and advanced structure. The efficient insertion and searching. So we'll talk about it in the algorithm class, class, but insertion, I'll show you why, insertion is fast and searching. It's two things that are pretty fast. You can add things, like I mentioned, insertion, you can add elements pretty quickly, and I did again on the background. Usually arrays or linked lists are used to represent. So Java would, still have, there isn't really a, like a core tree data structure. It's still the same arrays, but like we talked about hash tables, right? A hash table isn't really a fundamental data structure. It's it's abstract, just like trees. So usually those abstract data structures, they use some concrete data structures. Remember, we talked about abstract and concrete is arrays and linked lists. Abstracts are hash table trees, and that's basically uses the concrete data structure on the back end to represent the the functionality. So there's still arrays or linked lists I use, but trees, the framework that you use like Java, they'll do a lot of manipulations. Like remember we talked about hash tables last time. Hash table is a array on the background, and Java will create a function that you create a you insert an element in the hash table, the key value pair, and it will basically take that key, remember, and will create an integer in the background. You don't have to deal with an integer index, and then it'll insert your element in the array, and all you're gonna know that you're gonna say it's some kind of a key, and key could be anything like a string, like any string could be a key, or any other value could be a key that, but in the background Java will convert it to an index and store it in the array. So same thing is going to do for the trees. It's going to have arrays. It's going to do some complex logic to create a tree data structure that you can manipulate, but in the background it's linear data structure. So pretty cool stuff. But because remember I talked to you about how the memory is created, right? So in the memory, remember, it's a spreadsheet. It's basically like it resembles a spreadsheet. It's cells in the memory cells, and each cell, you can traverse cells linearly. The cells could be all over the place, and that's your linked list, right? There's a connection between cells, but that's it. There isn't really a tree there. You can't really create a tree in memory. All you can do is use something like a linked list to connect elements, and you can remember the connection. And if you have Java remember those connections, you could create concept of like a tree or hash table. So important to understand. I think it's pretty cool because some people think there is like a actual tree in the memory that happens. So all right, so where are we? So let's talk about the actual what comprises a tree. I assume you guys haven't really dealt with trees in this class yet, right? In QA class. So
Not really.
not really. Okay. So usually a tree will have a root. So that's just kind of the head element, right? The root of the tree, or kind of the first element, right? So any tree has a first element. So basically it needs to represent kind of the root node. And then there are different trees, and we'll talk through. There are trees that have multiple children. There's trees that have like binary trees that have two children. They all have different uses for for real life. So there's a lot there, but basically you can think of a tree as a root, and it has basically edges, and edges is the connection, right, in memory, or conceptual connection between an element to another element. These are called the edges, right? And then anything that comes off the root it can be considered a subtree, right? So there's a subtree within the tree. So basically anything is a subtree, and then you can insert those. We'll talk more about that, but basically a root connects to children, and the children are, if there are any two children of a parent, just like in real life, are called siblings. So any children of the same element, like here, or F and D of B, or D, E, and F of B, they're considered siblings. So as long as they have the same parent, they're siblings, right? Like brothers, sisters. And then the last node that doesn't have any children is called a leaf node. So basically, if there's no other continuation, that any node that has no children is a leaf. So hopefully pretty simple, right? It really resembles the actual trees, but I think of it as a tree that's on upside down. If that helps, right? The root is usually underground in these computer science trees. It's up top, and then everything is kind of go down. But if you really flip it, then it's a real tree that you see outside. It's like a root and branches and more branches, and then like leaves. Obviously leaves, they don't have anything growing out of them, so I guess that's how they named all of this crap. So all right, so as you can see, this creates ability to relate a lot of items, right? You can create multiple relationship, which are super helpful in any social media, that type of stuff, or not only that, we will talk about examples, but you can represent a lot of different things with trees. You can binary trees, for example, they hold a lot of algorithms. So you can create, actually encode algorithms for things like artificial intelligence. They use trees, I read, to create, to basically teach robots and others to have algorithm, because each kind of the child could represent some kind of a option, right? So you have kind of a question option, if this happens, then go down this route, right? So it gives an options, right? So a question, answer, and if this happens, do this. If this happens, do that. And if this happens, don't do anything. That type of stuff. So you can encode, very interesting logic in the trees, and we basically encode these, upload these behaviors for AI models to in the trees. So it's kind of, each thing is a kind of an action, right? And some type of logic represented in there. So that's being used, I know, interesting stuff. But like I said, the social networks is a perfect example where they use trees to represent all of your and this could also used in the databases as well. So the graph databases are very related to trees. So if you guys are mainly dealing with relational databases, I assume, for this class, right? So MySQL, all of that stuff, that's a relational database. So you have a kind of tabular format, right? You have values that are rows and columns, that type of stuff. you know, in the graph databases that are modeled after this tree data structure, you basically have these nodes, right? So you have basically you can store all of your you know, social network you know, users in there, and then the databases will provide that a relationship. So then you can traverse, right? So if you need to find all of the, you know, your connections that work at a certain company, then you can just traverse your connection and then you know, do some kind of a logic if their company attribute equals whatever, Microsoft or something like that. So very cool stuff. Okay. So I think we covered a lot of this. So that's a parent node, right? Predecessor, child nodes, successors of the parent, siblings are same parent, same. They have the same parent. So path is a number of successive edges from source node to destination node. So path is like, so if we go to from root to the age, the path would be 1, 2, 3, right? So it's how many edges, and that's basically a path there. Height of the node, height of a tree, depth of a node, degree of a tree. We'll cover those later in our algorithm, but basically it just kind of shows how far, how many connections. So you can use that for things like how many connections you have. For example, on like LinkedIn, you can use these elements to kind of traverse and show like how depth of your connections, right? So, or how many connections maybe in some kind of you know, those sites that Ancestry, right? Ancestry.com, they represent like the degree that, you know, of relationship, right, between you and some person. So they kind of have these trees, and if you are related, right, so let's say you're here, right, and that person is G, they can you know, use these principles to kind of understand, okay, well, maybe we have the same ancestor, right, and the ancestor has a child. So, you know, and then they can kind of count the edges and figure out that you are, you know, whatever cousin, like 17th cousin or something like that. So that makes sense. Yeah. So so basically that's really what they're used for. And when we talk about types of trees, I mentioned that a bit, but there are general trees. General trees really don't have any, you know, you have any number of siblings. So you can have a root with like 100,000 siblings and stuff like that, million, it's fine. That's usually a general tree. There are no specific number of siblings, that type of stuff. Binary tree, I wanted to mention binary tree, each element has exactly 2 children, so no more than 2 children. So, and like I said, they could be used in logic. So yes, no type of logic could be represented with binary trees pretty well. So, you know, that's or anything that has a binary answer, right? 0, 1, that type of stuff could be we could use you know, the binary tree to upload, so create like a logic and upload it into something, right? Upload it into AI algorithm or something like that. So I don't know, I'm not going to go through other ones, but you know, just to show you that there are a lot of different trees based on different purposes. So, and like I said, we'll talk more about some of these things when we talk about trees in the context of really understanding how the algorithms work to traverse the trees. So that's where we're going to talk about the binary search and that type of stuff. Because as you can see, trees are really good at organizing data. For example, if you have a lot of data and you can organize it in trees in a way that, if it you could simplify. So instead of going through a million elements and searching for some thing, you can say one side of the tree satisfies one condition and the other side of the tree satisfies the other condition. For example, maybe one side of the tree is people under a certain age, let's say under 40 years old, and the other side of the tree over 40 years old, right? So you could do that, and then you can take advantage of searching, right? We talked about efficient searching, because in the trees you can have that binary search. So you have that condition, and then you either go search one side or the other, but you don't have to go through all of the records. So tons of variations of the usefulness of the trees with a lot of when it comes to a lot of data. So. All right.
In which cases we or developers can can create such kind of nested list or tree structure?
Oh, well, when they need to represent that a relationship, right? So if they need to represent an element that has a relationship to multiple other elements, and that those other elements may have some kind of relationship to a bunch of other elements, right? So just kind of like this, right? Anything that the satisfies this type of relationship, that's where you'd use a tree.
Can you come with some particular example, because it's a bit confusing for me?
Sure. Well, like I said, the best one is a social network, right? So you can't really represent social network by using an array, right? Because an array, every element is really doesn't know anything about anything else, right? Element, you loop through elements, but element A only knows that there is a second element B. Element B knows there is a C. C knows D, but element A doesn't have relationship to XYZ, right? You have to loop through those. It's not direct relationship, so you can't really represent it. So that's where it could be used, like social network, anything that's where elements have direct relationship with multiple other elements.
Okay, thank you.
Mm-hmm. Any other? Any other questions? Sure. So that's really, that's trees. And like I said, we'll go more into those. So switching topics a bit, and so we're gonna start talking about algorithm. It's a lot there, but we last half an hour, I want to kind of talk about what algorithms are, and what's why you want to learn them, and we're gonna talk about the first one, and we'll leave with a homework assignment for practice, but I don't think you're gonna have time to do that in class because it's pretty a little involved, but so what algorithm I learn them and what type of algorithms are there. Algorithms are really a set of operations, right? So you do algorithms every day in your real life, right? So you wake up, brush your teeth, take shower, whatever you do, that's usually an algorithm, right? You follow a set of instructions. So it's really the list of same thing here. It's a list of operations that can done by the machine. So uh, and so nothing different here. So that's what an algorithm usually is. It's a way of solving some problem, right? So in computer science, in programming, a lot of problems have been solved. So you don't have to always think, okay, how do I do the search if you have dealing with a lot of data and you need to search for something, and you don't have to always reinvent the wheel. It's great that if you're thinking about innovative ways, so certainly I welcome that. That's great, but you don't always have to reinvent the wheel. So basically, the problems have been solved, right? So looking for a number or an element in a huge pool of data. Sometimes you could be like, well, how do I find it faster? My program just runs pretty slow, and that's been solved in algorithms, which we're going to learn, and you can apply. And obviously it's used for computing, data processing, reasoning, any type of things, right? Like I mentioned, reasoning trees are good for creating the reasoning structures for some of the AI algorithms out there. So really cool stuff. Why is it important? Well, you need to understand, right? Sorting, searching, traversing. Those are things that you're going to be doing all the time. So, you need to know how to do it effectively. Unless you work for a company that deals with little data, you don't care. But hopefully, you guys are going to work for large companies that deal with a lot of data, and that's where the the whole challenge comes. Anything there, banks and all of that stuff obviously has billions and billions of data element transactions, points of data and all of that stuff that you apply algorithms on when you manipulate the data, whether you're searching, traversing, doing that type of stuff. So very common to use the algorithms on those operations so they're effective, fast. And then you're going to be leveraging a data structure. So that's why we have this portion of the class following data structures. You're going to be leveraging data structures in these algorithms. So they're related. So we're going to be showing how to search for a number in like an array effectively and that type of stuff. So we talked about some of the techniques, just looping, right, for a element, and usual ways just going through each element of the loop and doing some kind of if statement, right? If but imagine you have hundreds of thousands or millions of data elements. That's obviously a waste of processing power, waste of your the time, and and your program may become very slow. So you need to be able to apply some algorithm to do it faster. So that's what we're going to be learning. And then the job interviews, that's really common to do, searching, that type of stuff, because they want to know the fundamentals, especially I mentioned last class, right? We're talking about some of the job preparations for you guys, as you don't have really a lot of experience to talk about other than this class and potentially some of your freelance, personal project, which I certainly encourage you to take on. But they're going to be looking for your understanding of the principles of programming, software engineering, quality assurance engineering, because the employers are looking for knowledge in the lack of best experience until you get the best experience. So you're going to need to know that. All right. So hopefully you're all interested, basically all of this stuff is going to take us through the end of the course into May, right? So we have a little bit less than a couple months to go through this. So now the type of algorithm, right? So what type are there and what the applications are? There are recursive algorithms. Have you guys heard of recursion? What that is?
No.
No? Okay. So that's basically that's very, very interesting thing. I think you're gonna have a lot of fun with that. But recursion is basically a function calling itself. So you write a function, it does something, and then it calls itself. So with some different data. So we'll look through those. A lot of applications of recursion algorithms there. There's dynamic programming, so that's really kind of the more modern application of algorithms. Like I said, trees are used a lot in the dynamic programming, and that's really giving into a machine a set of instructions. So the machine, based on the inputs, can choose what instructions to follow. So it's not really kind of hard-coded if and else. There is a lot more, it looks at the data, right? So dynamic means, it depends on something. It's not just hard-coded. So it'll look in the data and apply different things based on the certain conditions. So really cool field. And, it's good for, even if you guys don't necessarily start with those type of jobs, but anybody that's interested in having a career in computer science, it'll be interesting to know all the things that are available, because as you grow as a QA engineer or developer, you want to know what's, if you're truly interested, what are the fields that you can pursue. So I think that's pretty cool. Backtracking, divide and conquer. Divide and conquer is what we're gonna start with, because that's really super, super important in terms of searching and sorting. That's an algorithm that will cut the linear time of operation into improve the linear time into something called O log of n. So O of n transforms into O log of n, and basically that means, so if you have an data structure, an array, and you're going through it, divide and conquer can potentially take the amount of elements and maybe divide it by half or something like that. So you're not, it's a little bit better than kind of linear time. So that's very widely used. And then brute force and randomized algorithms. So we'll touch on those, but we'll start with divide and conquer for today, right? So a bunch of things there, and don't get discouraged. It's a lot, but we won't have to get into each one, in huge level of details. I'll just cover the stuff that you're gonna need for your work and you're gonna need for your interviews, and I won't, confuse you with just like the very, very rare algorithms that are used by some mathematicians and writing programs and that type of stuff. So don't worry about that. Okay, so let's talk about what you already know. and you already have an algorithm that you've been already using, right? I just mentioned a few minutes ago, going through an array, right? And you do a lot of searches in your code. You're going to do a lot of searches. That's kind of looping through an array of data is the most common thing you do, whether you're writing functional code or you're doing some QA analysis. You get the data and then you loop in, making sure that some elements match your expectations and all of that stuff. So that's actually a linear algorithm. So usually kind of the way it goes, right? And that goes for all the algorithms out there. You have steps. So algorithms are represented as steps, right? So like a math program or something like that, math problem, it's steps. So step one, you traverse the array, right? And so you write your for loop, while loop, or whatever other loop, and then inside of that traversal, you match the key element. So what you're looking for, right? So if you're looking at an array for value number 5, you're matching each element of the array to that key element, which is number 5. So if the key element is found, you return the index of the position of the element, right? So I think I had you do enough of those exercises where you did some type of indexing and that type of stuff. So you find the number, or find the element, and return an index. So as you can see, it's you already been doing algorithms without even knowing it, or maybe you knew it. And if nothing is found, for example, you return -1. So all of that is a example of an algorithm. So that's a linear algorithm. You go through each value, and worst case scenario, you go through all of the values and nothing is found, you return 1. As you already know, we've been discussing, since you guys are fundamental software engineers, you already know that this type of stuff has a ON time complexity, because in the worst case scenarios, you have to go through the entire data structure, right? So that's the worst case scenario, and that's what makes it a linear. So the more elements you have, the more the proportion is gonna the time is gonna take is gonna rise. Okay, so this is a linear algorithm, very basic. You guys already know. Any questions so far on anything we've talked about? No. All right, so this is just what I talked about. Very, very common thing that you guys have seen many times already. So ON complexity. Now, so I mentioned O log n, right? So that's really where the trick is, and why we have this divide and conquer algorithms. So don't worry about the nested loop ON squared, right? I mentioned the ON squared, which is kind of nested loops. That's why every time I give you guys these exercises, I encourage you to write a single loop. So it's faster. But O log n is even faster than O of n. So this is O of n, right? And you go through each element array.length. Now here, the trick is you have a choice of which element to perform the action on, right? Here, you don't have a choice, right? You're going through all the numbers in the array or in any data structure you search for, right? So you go for the entire loop. There's no choice. You go one by one by one, and you keep going. You just do a condition for each element. So no choice. Go through the thing. When you want to improve this, you create some type of algorithm that gives you a choice. Do I really go look for the next element, or should I go look at some other element? Because your array, you can you can do something, with the data that won't make you go through entire length of the array, right? So that's where the trick is going to come from. And when you do that, you can basically break up your data structure, your data into certain subsets, right? And then you need to choose one path out of several. And, by doing that, you slightly reduce, or not so slightly, maybe in a major way, you reduce improve the performance of your, of your search. So again, it's not going to be instant, but likely, but it's still going to be better than going through every element. Very, very powerful technique. So you're gonna look for that it's called O log n. So remember that for your interviews and that type of stuff. There's ON, it's a linear, and O log of n, that's slightly, it's better than linear. It's basically, more optimization of the linear algorithm. Right? And I don't know how else to call it. Maybe maybe there is a name for this. Logarithmic. So logarithmic. I think that's what I was going for. Yeah, so logarithmic running time. So, cool. And all right, so achieved using divide and conquer strategies. So again, divide and conquer means you divide the data and then you conquer by dividing it. All right, so this leads us to a search algorithm that we're going to cover first in this class, and it's called binary search. So binary search is a variation of divide and conquer strategy. So divide and conquer type of algorithms. It has an assumption that elements are sorted. So for that to happen, right, you have to sort your array. So the way the sorting does is really happens is outside of this algorithm. Basically, it's a prerequisite for this algorithm to be activated, to be useful. Values have to be sorted, and they can be sorted. It doesn't have to be integers, right? So if you have an array or a linked list or any other list that stores customers, it has to be sorted by whatever attribute you use to sort those customers, whatever you search for. For example, if you are looking for customers that are, that are like, certain age, right? Maybe you're doing some kind of marketing thing and you're certainly looking for customers with 25-year-olds, you want to market some new product to that demographic, then you would want to get that array sorted by the age of the customers. How that happens, usually you would write a query to get the data from the database in that way, right? So that's kind of the most common way to get the data into your application that's sorted. You'd use a query. I assume you guys have been using queries to query the database, right?
We haven't covered SQL yet.
Oh, you haven't covered SQL yet? Okay, so that's going to come, but you'll have an ability to go through and write those queries, select customers where blah blah blah, and order by like age or something, or something like that. And then when you have using Java, you basically get the the results of the query, and you create objects of the customer and for any type of processing for your application, which is going to be whatever your application does. It puts it on the website or does some kind of a search and all of that good stuff. So anyway, sorting is a prerequisite for the divide and conquer. So how this happens? So let's say you have a sorted, and we're going to use integer arrays as a basically the example here. So because it's just simple, right? So you have an integer array from like 1 to 10. So what you're going to do is to divide and conquer. Let's say you want to search for a number in the integer array of 1 to 10. You want to use look for a number 2, for example. All right. So usually you would go and start going through the loop, right, and just going through the number for the looking for each number if it's number 2. So here you can be faster. Obviously, if you have a sorted array, you could tell that you don't really, if you apply that kind of a brute force principle, right? If you look at the array and it just has 1 to 10, and if you were doing it without the computer, you wouldn't just go, you would look in the, that 2 is, less than like 5, for example, right? So you wouldn't go and search after 5 because you just know that 2 is less than 5. So you're gonna kind of look at even naturally without telling the computer. You have to look at the first half of the numbers for your 2, and then you already know that 2 is less than 3 and so on. So if you're given that array, and you're not going to go to the right side of it looking for 2 because you already know it's on the left side. So that's what really the divide and conquer is, right? You find the pivot, and the pivot is you just really divide the array by half and compare target value with the value at the pivot point, and that has that log complexity. So let's look at that. How this happens. So let's say you have an array that looks like this, and you have 15 elements in there, right? So, from 167 is the last element, right? So basically what you're going to do here, you're going to keep dividing. So let's look for the number 13 on this, right? So what we're going to do is basically take the length of that and divide it by 2, and that gives us 7 whole number. So basically you get to the element at the index of 7. So 0, 1, 2, 3, 4, 5, 6, 7, and that gives us 16, right? So, and then what you're going to do here is basically your algorithm is going to say, is value at the index equals greater or less or equals to the value you're looking for. If it's less, then you go do the same thing on this side. If it's more, if your value is greater than 16, you go here, all right? Do the same thing. You already wrote the code. So here we say, okay, 13 is smaller than 16. So you do the same thing, right? And that's where recursion is going to come in. We're going to talk about recursion. Remember, I told you recursion is doing the same, operation and just different set of input, but same operation. So operation and set of inputs. So here you say, okay, 13 is less. So we do basically the left side of that. So we're going to say, okay, take the array from here to here, right? So, basically, take this array as the left side of the array as a next search, set. here you do the same. Okay, you know, divide this by 2, and you know, look for the middle. So the middle would be 4. I'm sorry, the number 3, element index 3, and that's the value 8. So 13 is actually greater than 8. So, you know, we're gonna look from, you know, from here on the right side, right? So from 12 to 16. And then here we do the same thing, and you know, we end at this side, 12 and 13, and then, you know, we do this until the actual pivot is equal to the number. So as you can see here, we take you know, elements 13 as a pivot. You know, and then 13 becomes that's you know, that's where the number is. So that's really kind of the core of that, right? So we'll go in the next class, we'll go and start preparing for this homework. So we're gonna actually implement the logic to do this. Unless, you know, if you guys want to prepare, you know, if you have time to actually do something like this, I'll post this, but you know, I'm planning kind of doing this together. So I wanted to introduce the it's skipping my mind. What is it? The I guess talking too much. The recursive search here. So you need another example of a recursion to kind of do this, but you don't have to do this with recursion. It's just more elegant. But basically, as you can see, if you're looking for number 13, if this, you know, wasn't really sorted the way this is, you would have to just go through potentially, you know, 15 numbers. Here you do, you know, 1, 2, 3 comparisons. That's it, right? So potentially, you know, 15 or 16 comparisons versus, you know, 1, 2, 3, and well, 4 comparisons. So as you can see, you know, the number of comparisons or the operations you're doing is significantly less. And that could matter for huge data sets. So that's what we're gonna do. I'm gonna kind of look at how to implement this in the actual, how to implement this algorithm in the actual code. And we're gonna actually talk about recursion itself, how, so we have Russian dolls here, right? And as you can see, each Russian doll has a, you know, another set of dolls inside. So that's what the recursion does basically. So should be hopefully near and dear for you guys. But as you can see, you know, this, but you know, potentially it reduces the number of actual comparisons you do by just taking subsets of the array. You basically go and you say, I'm looking for a number. I know these things are, you know, sorted. Taking half is the number on this side or that side. If it's on this, on the left side, throw away the right side. So throw away the right side. Now you have all these numbers. Again, you're doing the same thing. All you're doing is, what's the middle element? You choose the middle element and you're saying, okay, is the number on the left or on the right? Same thing you just did there. If it's on the, if it's larger than the middle element, you know that you don't really need to look at the all the left elements, throw them out, right? So you take only these guys here, and you keep doing that until you get to the end. So as your data becomes smaller and smaller, eventually you're gonna, you know, you're just gonna end up at your number, and your middle element is going to be your number. All right, any questions and we're not finished, right? Like I said, we'll continue this next week and kind of go through the coding of this, but feel free, I'll post this. Feel free to start thinking about how would you do something like this. If you, for any bonus points, if you feel adventurous, try to implement this in the code, maybe using this example and assuming that the numbers are sorted. Any questions on that approach? A little confusing?
Not really.
Not bad? Okay, excellent. All right.
What kind of homework should we do?
So just let's see. Think of this, right? Think of this if you can, right? Implement binary search and array of elements, input sorted array. So imagine sorted array like this, and there is a target value. So basically, if we look at the actual algorithm, so you'd say, take, so divide length of array in half and look at middle element, right? So compare element with target. If element less than target, search left side array. So element -1, right? So you go to the left. If element greater than target, search right side of array element plus. I'll do that. Right. Huh? All right. So this is really the algorithm for binary search. So if element is less than, if target is less than the middle element, go to the left. If it's greater, go to the right. If it's equal, you're done. See if you can do this without using recursion. So, just you're using a function. And then we're going to introduce recursion next class. I'm going to post this in Slack. I'm going to post the actual, in the code wall, I'm going to post the actual algorithm. So try to do that. It should be easy, right? You basically get the array, you have your input is going to be, so function is going to take, array of int and target num, and you can assume that array of integers is sorted. Okay, and then basically just there isn't really a loop, right? You do well. I'm not gonna just work through it. Let me know if you have any questions. Sound good?
Okay.
All right, have fun. Have a good weekend. I'll see you guys on Tuesday. We'll look at this.
Thank you, Igor.
All right.
Thank you.
Bye.